Hello everyone, my name is Bhiman. I am a PhD student in computer science at the University of Pittsburgh, and today I will be presenting our work resolving UnderEdit and OverEdit with iterative and neighbor-assisted model editing. Model editing has emerged as an efficient alternative to fine-tuning for factual knowledge updates in LLMs. However, current model editing algorithms face two major challenges: UnderEdit and OverEdit. These challenges are demonstrated in this given example, where an edit to update the producer of iPad from Apple to Honda fails, which we categorize as UnderEdit. On the other hand, OverEdit signifies the unintended change to the neighboring knowledge, like the developer of the iPhone. To overcome these challenges, we propose two complementary solutions: iterative and neighbor-assisted model editing. However, to better understand how and why these methods work, first we need to understand the design principle behind these model editing algorithms. In this work, we focus on model editing algorithms that follow the locate and edit framework. As the name suggests, first we need to locate the factual knowledge inside the LLM. Here, we visualize the computational model as a grid of transformer blocks attending to each input token across layers. The causal tracing comes in handy here. It specifies that MLPs of the early layer attending to the last subject token are responsible for factual recall. Following our previous example, iPad is our last subject token, and transformer blocks attending to it from layers 3 to 4 has been identified as the causal range responsible for recalling the object Apple under the relation produced by. Once this range is identified, it remains common for all factual knowledge last subject token. Then comes the model editing algorithm, which performs the editing in two stages. In the first stage, known as optimization, it learns an ideal hidden state for the last transformer block in the causal range, such that the model starts generating the desired new object, which is Honda in our case, keeping the subject and relation intact. Then in the next stage, by identifying the delta in the learned and the initial hidden state, it propagates that delta to the MLP weights via rank 1 update. However, instead of a single transformer block, the delta is propagated to the entire causal range. Hence, we categorize this stage as spread stage. Here, the magnitude of the update is inversely proportional to the distance from the last transformer block. On an abstract level, an edited model after these two stages looks like this illustration, producing the desired output. Now we ask, failure in which of these two stages leads to UnderEdit? Intuitively, the goal of spread stage is to mimic the optimization stage. Therefore, we can ideally expect both stages to generate the same hidden state. However, we hypothesize two reasons for UnderEdit. First, the weight update by spread is not sufficient to reproduce the ideal hidden state. Second, the optimization state itself is unable to learn a hidden state, leading to successful editing. To tackle both these reasons leading to UnderEdit, we propose iterative model editing. As the name suggests, we run the editing algorithms for multiple iterations. To verify the reasons and the success of our proposed method, we compute the perplexity of the desired output for both the stages. As observed in the figure on the right, after the first iteration, there is a perplexity difference between the two stages, verifying our hypothesis of weight update by spread being insufficient. With successive iterations, the gap reduces, eventually leading to successful editing resolving UnderEdit. In the case of OverEdit, the algorithm has been told what to edit but never what shouldn't. Prior work has shown that fine-tuning with such examples prevents unintended knowledge updates, and we hypothesize the same for model editing. Therefore, we propose neighbor-assisted model editing, where along with maximizing the likelihood of new knowledge, we also maximize the likelihood of the neighboring knowledge. And the good thing is, We just need one such neighboring example. We evaluate our proposed methods on 4 LLMs and 2 benchmark datasets in terms of efficacy, generalizability, specificity, and a combined score, which is the harmonic mean of the three. Since our approach can be applied on top of any locate and edit model editing algorithm, we chose 4 most popular editing algorithms to showcase the effectiveness of our work. Now moving on to results, here we compare the first iteration of model editing algorithm represented with blue bars with the kth termination iteration of iterative model editing approach applied on that algorithm, represented by the orange bars. As you can see from the plot, iterative model editing improved performance across all editing algorithms and models. Next, we compare the kth termination iteration of iterative model editing represented with blue bars with that of neighbor-assisted model editing represented by orange bars. Here, neighbor-assisted model editing has been applied on top of iterative model editing. As observed, neighbor-assisted model editing outperformed across all baselines. This showcases the complementary nature of our two proposed methods, leading to best performance. Finally, I would like to conclude with the takeaways that our work uncovered two major challenges in locate and edit model editing algorithms and proposed solutions to them which are applicable across all locate and edit model editing algorithms. Do check out our paper for more information. Thank you so much for your time.